In this session, we are going to see about different crystal systems and different types of crystal structures, basically about a different classification in a cubic structure. First, we can see how the crystal systems are classified and under what basis it is being classified. Now, there are 7 crystal systems in whole of this universe. So, when you are going for any of the shapes that comes under this 7 crystal system, the first and the basic is a cubic, which is also called as an isometric crystal system. Then a tetragonal, orthorhombic, trigonal, which is also called as rhombohedral, monoclinic, triclinic and hexagonal. So, how we are going to distinguish these types of crystal system? On what basis we are going to classify this? So, it is basically on the primitives and the interfacial angles, so what we have seen in our previous session. So, that is A vector, B vector, C vector, alpha, beta, gamma. So, how we are going to classify this crystal systems? So, that is being seen in our chart. So, these are the 3 different types of lattices, which we call it as Bravais lattices. So, that means once again the 7 crystal systems are being classified into 14 types of Bravais lattices. That means they are being specialized. For example, a cubic is being classified as a simple cubic structure, a body centered cubic structure and a face centered cubic structure. So, everything is because of the orientation of an atoms. So, now we can define what are Bravais lattices. So, the 14 types of unit cells under 7 crystal systems are what we call it as the Bravais lattices, or we can say that 14 possible ways in which 7 crystal systems can be explained. That is what we call it as Bravais lattices. So, here we have a notation PIF. So, what is meant by P? P is what we call it as a primitive or simple. I is what body centered, F is face centered and C is what we call it as in side centered, or sometimes it is called as the base centered. So, this is a generalized measurable quantity which is used in an international system. So, now we can see how we are going to classify the 7 crystal system based on this parameters. So, just by seeing this parameter, that is the interfacial angles and the interfacial length, we will be able to adjourn what is a type of crystal system we are going to see about. The first is a cubic. So, here we can see that when A is equal to B is equal to C, that means when all the sides are equal and the angles alpha is equal to, beta is equal to, gamma is equal to 90 degree, that means it comes under a cubic system. And what about the tetragonal? So, one of this length would be not equal, that is A is equal to B not equal to C, alpha is equal to, beta is equal to, gamma is equal to 90 degree. So, when these condition is satisfied, it comes under the tetragonal system. And what is orthorhombic? All these 3 sides are unequal, that is A not equal to, B not equal to, C, whereas the angles are equal to 90 degree. They are mutually perpendicular to each other. They are called as an orthorhombic system. And what is so unique about this orthorhombic is that this is a only crystal systems which can exist in all these 4 types of Bravais lattices, that is a simple, base centered, body centered and face centered. And hexagonal, so which is a very closely packed structure in which we say that A is equal to B is equal to C, alpha is equal to beta is equal to 90 degree, whereas gamma is equal to 120 degree. So, when these parameters are satisfied, we call it as an hexagonal structure, which we call it as a closely packed structure. And we go for monoclinic. From the name itself, we can understand that monoclinic, that means one of the angle is not being equal to 90 degree. That means A is equal to, B is equal to C, which is A is not equal to, B is not equal to C, whereas alpha is equal to, beta is equal to 90 degree and gamma not equal to 90 degree. And when you go for triclinic, all the angles are unequal and the sides are also unequal. So by seeing these parameters, we will be able to ascertain what type of crystal structure it has. So this is a very important quantity as for the crystal orientation is considered. So now we are going to see about the different crystal structures. So before going on to the crystal structure, there are 4 important characteristics what makes the crystal structures to be unique, what makes the crystal structures to be different. So when we calculate all these parameters, and as I said that it is enough if we study about a unit cell. So when you study about a unit cell, it clearly explains the entire crystal structure. The first and foremost characteristic is number of atoms per unit cell. So as the name implies, we know what is meant by this number of atoms per unit cell, that is the number of atoms which is present in a unit cell. So already I think we can recapitulate. So when a unit cell contains only one atom, it is called as a primitive unit cell. If it is more than one atom, it is called as non-primitive unit cell. So from that we can ascertain what type of crystal structure it has. So this is the first and foremost characteristic of a crystal. The second characteristic is what we call it as a coordination number. So from this, a coordination between the atoms which gives a binding property of a crystal. We say a crystal structure is closely packed, a crystal structure is loosely packed. So how we are able to distinguish that? That is because of this coordination number. So how we define this coordination number? So it is going to be a number of equidistant atom for a particular atom under study. So you can consider any atom and how many neighboring atoms are present for the particular atom considered. That is what we call it as a coordination number, which is an important characteristic of any of the crystal structure which gives the property of binding for a crystal. The third is the atomic radius. So as we all know that a radius, in the sense we say that a half a diameter is what we call it as radius, but here we define this in a different manner. So it is going to be the half the distance but between the nearest neighboring atom. So it is not within an atom we are going to calculate, so what it is called as an atomic radius. That means it is going to be half the distance between the nearest neighboring atom in a crystal. It differs from one crystal to another crystal. It is not going to be the same for all the crystal. And the last property is what we call it as the atomic packing fraction, or in other terms we call it as a packing density. So actually this is correlated with the coordination number. The coordination number is mere a number. It just says that whether it is being closely packed or loosely packed. But when we go for this packing density, it exactly gives what is a vacancy that is being present in a crystal. So whether we can add any more atoms or we can, that means actually what is the use of studying this packing density, because already we know that from the coordination number it is going to be a closely packed. So why we go for another parameter, packing density? Actually when you are going for a semiconductor, you must have come across a term called as an extrinsic semiconductor. So extrinsic is nothing but impure form of crystals. So when you go for the impurity, that means we are going to add a dopant. Whether a dopant can be added or it can be removed, whether it is a donor or an acceptor, that can be determined using this packing density. And this packing density can be easily determined by using a relation, so which is defined as a ratio of a volume occupied by the atoms in a unit cell to the volume of a unit cell. Once again, if it is a cubic crystal, it is very easy to calculate volume of a unit cell, which is nothing but A cube. Whereas when you go for any other structure, for example HCP structures or any crystal system structures, we have to first calculate the unit cell, then we can calculate the volume occupied by the atoms in the unit cell. How to calculate the volume occupied by an atoms in a unit cell? It's nothing but volume of a unit cell, which is nothing but A cube for a simple cubic structure. If it is going to be a volume of a sphere, what is the volume of a sphere? It is 4 by 3 pi r cube into number of atoms per unit cell. So first we are going to calculate how many number of atoms per unit cell. Just multiply with the volume of a sphere, that will give you what is a volume occupied by the atoms in a unit cell. That is how we calculate the packing factor or packing density. Now we go for an important classification under a cubic structure, a simple cubic. body centered cubic and face centered cubic, and in addition a very important packed structure which is an hexagonal closely packed structure, so which is under our study. So first, what is a simple cubic structure? So how we are going to explain a simple cubic structure? A simple cube is nothing but a cubic structure in which the atoms are present only at the corners of the cube. So how many corners are there for a cube? There are 8 corners for a cube. So all these 8 corners is occupied by the 8 atoms. So now we can see how the atoms are being oriented. So now you can see that only 8 atoms which is being present only at the corner. So this is what we call it as a simple cubic structure. So first we had drawing a simple cubic structure. Now we are going to calculate all the 4 characteristics of a simple cube. Number 1, number of atoms per unit cell, and always mind it. So here the corner atoms means this is for a unit cell. So when you are going to consider a single crystal as such, first we have to find what is the contribution of each corner atom. So for example, this particular corner atom, so this is being a unit cell, I have considered an entire crystal structure. This is what is your corner atom. Now we can see that each corner atom is shared by 8 other unit cell. 1, 2, 3, 4, 5, 6, 7, 8. So when this 8 atoms, that means the contribution of each corner atom is going to be 1 by 8. So how many number of corner atoms are there? 8 corner atoms are there. So the total number of atoms in a unit cell is going to be contribution 1 by 8 into the number of atoms into 8, that is equal to 1. So when the number of atoms per unit cell becomes 1, it is called as a primitive unit cell. So this is where comes the primitive nature of a crystal structure. The second important property is the coordination number. So how to find the coordination number? It is a nearest neighboring atom which is surrounding a particular atoms under study. Now we are just considering one of the corner atoms. So because here only the corner atoms are present. So when we are considering this one corner atoms, so we can see the nearest neighboring atom which is being denoted by a red color line. So we can just count how many red color lines are there. So it's 1, 2, 3, 4, 5 and 6. So these are the nearest neighboring atom for a particular atom considered. So we can calculate this coordination number not only considering this center atoms, we can go for any of the corner atoms. So whatever atoms we are considering, it becomes the same, that is 6. So the coordination number is 6. So which gives us an idea that a simple cubic structure is not being tightly bounded, it is not being closely packed. This gives an idea. The third important characteristic is the atomic radius. So I think the atomic radius calculations is very simple from this diagram. So this is going to be an atom which is being corner. This is also another atom, and here we can see that each corner atom touches each other, and this length, that is from this point to this point, we call it as an edge length, which is represented by A. So the radius, how to find the radius? The radius is nothing but it's half a distance between the nearest neighboring atom. That means A is equal to 2r, or r is equal to A by 2. So the atomic radius for a simple cubic structure becomes A by 2. So this is how we are calculating the atomic radius for a simple cubic structure. The last and an important characteristic, so which is a packing density or a packing fraction of a simple cubic structure. So how to calculate this for a simple cubic structure? So this is APF, which is nothing but an atomic packing factor or an atomic packing density. So in order to calculate this, we must know what is the volume occupied by the number of atoms per unit cell and what is the volume of the unit cell. And as we all know that volume of a unit cell, so since it is a cubic structure, we know that A is equal to B is equal to C. That means we can represent that by A cube. A into B into C is equal to A into A into A is equal to A cube. So the volume of a unit cell becomes A cube. Now how to calculate this volume occupied by the total number? So first we are calculating what is volume of one atom assuming it's a spherical in nature, we know that atoms are spherical in nature. So its value is 4 by 3 pi r cube into number of atoms per unit cell. What is the number of atoms per unit cell? It is primitive in nature, so the value comes to be 1. So now we can substitute that in our formula. So it becomes 4 by 3 pi r cube into 1. So instead of r, we can represent that by an edge length. So as we know that as we have calculated, the radius for a simple cubic is r is equal to a by 2. We just put it as 4 by 3 pi a by 2 the whole cube. So now we substitute in our formula, which is small v divided by capital V, that is volume of atoms in the unit cell divided by volume of unit cell. We get the packing density to be pi by 6, which comes around to be 0.52. So which specifies that 52% of a volume of the unit cell is occupied by the atoms and the remaining 48% is being vacant. So this gives an idea. So that means approximately 50-50. That means we say that 50% is vacant in a simple cubic structure. So as we have already seen that a simple cubic structure is possessed only by an element known as polonium. This is the first structure. The second structure is, so this is how we calculate the packing density of simple cubic. The next structure is a body centered cubic structure, BCC. So from the name itself we can understand that there is a body centered atom which is being present in this crystal structure. That is how we are going to categorize this crystal structures. So first we can see the crystal structures, see how the atoms are being placed. So we can see that at all the 8 corners of a cube, the atoms are placed, and in addition there is a body centered atom, so which is being specified by a red sphere. That means here the corner atoms will not touch each other, rather the corner atoms would be touching the body centered atom. So that is how, so there is a variation. So this produces a variation in the radius of an atoms, what we are going to calculate. So first we can start with a basic, that is the number of atoms per unit cell. So when we are going to start off with that, and there are lot of elements which possess this BCC. So we can see that tantalum, tungsten, molybdenum, then iron, chromium, everything has a BCC structure. And here how to calculate the number of atoms? So we recapitulate our simple cubic. So first we have to see about the corner atoms. So there are 2 types of atoms present here. One is a corner atom, the corner atom, and the second one is going to be a body centered atom. The corner atom, in the sense each corner atom is shared by 8 unit cell, and hence the contribution of each corner atoms is going to be 1 by 8. So how many corner atoms are there? It's 8. So 8 into 1 by 8, so it becomes 1. And in addition, so it's not a primitive, we cannot conclude that it's a primitive cell. In addition, we can see that it has a body centered atom. So when you are having a body centered atom, so what we have to do is that we have to consider that body centered atom also when we are going to calculate the number of atoms per unit cell. So here what happens is that this body centered is not being shared by any other unit cell. It is being well within this unit cell. So its contribution is 1. So that means number of corner atoms per unit cell is 1 plus number of body centered atom is going to be 1. So 1 plus 1 is equal to 2. So this come under a non-primitive unit cell. The next one is the coordination number. So how to go on with the coordination number? So now let us consider the body centered atom. So how many nearest neighboring atoms are there? Which is going to be a nearest neighboring atom? So each corner atoms are the nearest neighboring atom. And as we all know that this 8 corner atoms is going to be the nearest, so the coordination number is going to be 8. So in vice versa, if you are going for a corner atoms, for a corner atom, body centered atom is going to be a nearest neighboring. So when you are considering 8 unit cell, that 8 body centered is going to be the nearest neighboring. So whatever is the thing, whether you are considering a corner atom or you are considering a body centered atom, so everything, the coordination number goes to be 8. So which is more than that of a simple cubic structure. So now we are going to see about a unique property, which is an atomic radius, which is not as simple as a simple cubic structure. So now we have to calculate the atomic radius for this. So how to go about the atomic radius? So now we are going to draw a diagonal. So we are considering two corner atoms A and B, and when you join AB, that is going to be the body diagonal of this BCC structure. And from there we are going to consider another face, that is the bottom face of this cubic structure, and another draw a diagonal which is a base diagonal. So now with this we will be able to calculate what is the atomic radius. So here we can consider that this A and B, when you are joining it, first we can use Pythagoras theorem. So as we all know that Pythagoras theorem, AB square is equal to AC square plus BC square. So we have to calculate what is AB square and what is AC square, and we know that what is BC square. BC square is nothing but A square. So how to calculate once again AC square? So we can calculate AC square by the formulation AC square is equal to AD square plus CD square. So once again this becomes A square plus A square is equal to AC square, or in other words we can say that AC square is equal to 2A square, or AC is equal to root 2A. This is how we get the value of root 2A by using Pythagoras theorem. So we are using this Pythagoras theorem twice, one for this triangle ADC and other for the triangle ACB. That's it. So once again when you are using this, we will be able to substitute, because already we have found the value of what is AC. Now substitute that, so it becomes root 2A the whole square plus A square is equal to AB square. So from that we will be able to calculate. And what is this AB? So here how to find this AB value? So it is nothing but this is a corner atom, this is a corner atom, this is a body centered atom, and this value is R, the whole radius is 2R, and this radius is R. So R plus 2R plus R is equal to 4R. So we have to be very careful when you are substituting this value. It should be written as 4R the whole square and not as 4R square. This is a common mistake normally we do. So 4R the whole square is equal to A square plus A square plus A square. So which would bring us 16R square is equal to 3A square, or we can just find what is R. R is root 3A by 4, which is different from that of a simple cubic structure, which is R is equal to A by 2. So depending upon the atoms that binding, the atomic radius also differs. It is not the same for all the simple cubic, body centered cubic and face centered cubic structure. So the last factor, which is a packing density. So what is packing density? Once again we recapitulate. APF is a volume of atoms in the unit cell divided by volume of the unit cell. Once again, since it is a cubic structure, we can substitute the volume of the unit cell as A cube, whereas here it differs because number of atoms per unit cell is 2 and volume of an atom is 4 by 3 pi R cube, and once again instead of R we have to substitute as root 3A by 4 the whole cube. So when we are finding this, computing this value, we will be able to get the value to be 0.68. So that means 68% is being occupied by the atoms, so which is more when compared to that of a simple cubic structure. The next structure we are going to see about is a face centered cubic structure. And here you can see that in a face centered cubic structure, the most of the elements are metal like gold, silver, copper, platinum, nickel. So they come under this face centered. This face centered cubic structure is also called as CCP, that is cubically closely packed structure. So once again we are going to characterize this face centered cubic structure. So first let us study what is FCC. So from the name itself you can see that it has a corner atom, in addition to it, it has 6 face centered atoms. So there are 6 faces for a cube. So in addition to 8 corner atoms, there are 6 face centered atoms which is being present in this face centered cubic structure. So first let us calculate the first characteristic, number of atoms per unit cell. So here once again there are 2 types of atoms. One is a corner atom and other one is a face centered atom. So first we can find for the corner atoms. Each corner atom is shared by 8 unit cell. So the contribution is 1 by 8. So since there are 8 corner atoms, the total number of corner atoms present is 8 into 1 by 8, which is 1. And we should not forget about this face centered atom. When you are considering this face centered atom is being shared by 2 unit cell, that is one below and other above. So when you are considering this is a unit cell, you just consider there is another cube over this space. So that means what? It is shared by this unit cell as well as the unit cell which is above. So that means its contribution is 1 by 2. So how many face centered are there? 6 face centered are there. So its contribution is 6 into 1 by 2, so it becomes 3. So now we combine the contribution by the face centered and the contribution by the corner atoms. So it is 1 plus 3, which is equal to 4. So the number of atoms per unit cell in an FCC structure is 4 atoms. The second characteristic is the coordination number. So when we go for this coordination number for an FCC structure, so it seems to be a complicated derivation or a complicated figure, but it's quite easy to understand. So now we can see that the sharing or by a face centered atom is being half, and we are getting the values to be 1 by 2 into 6 is equal to 3, and when we are combining with this we get it as 4. So how easily we can represent? So now consider this diagram. So when you are considering this diagram, I am just considering an atom which is being present at the corner of a unit cell. This is a unit cell. Now we can see that there are 8 unit cells, 1, 2, 3, 4, 5, 6, 7, 8, 4 below and 4 above. How to calculate the coordination number? So when you are considering this corner atom, there are 4 face centered atom here, so which is being shown by a small dot, that is the nearest neighboring atom, and here 2 on the top face, 2 on the bottom face, and 1 on the left, right, left, right. So totally in the same plane 4 atoms, above the plane 4 atoms, and below the plane 4 atoms. So totally 4 plus 4 plus 4 is equal to 12. So this is how we calculate this coordination number. So once again I tell this how we are going to calculate. So you can see that here is a corner atom. So for this corner atom, 4 atoms in the same plane, 4 atoms above the plane, and 4 atoms below the plane becomes the nearest neighboring atom. So this is a corner atom. So for a corner atom, the face centered atoms are its nearest neighboring atoms. So when we are calculating, we will be getting 4 plus 4 plus 4 is equal to 12. So which is the coordination number for an FCC structure. So when we have studied simple cubic, BCC, FCC, now we can just compare. So it was 6, 8, now 12. So which shows that the face centered is more closely packed when compared to a simple cubic or a body centered cubic. The last parameter is, as we all know, the atomic packing density and the atomic radius. So first the atomic radius. So it's very quite easy to calculate the atomic radius for an FCC structure when compared to that of an BCC structure. So here we are considering one face which is ABCD. So in this face we just draw a diagonal which connects A and C. So as we all seen in our previous explanation for BCC, so what is this distance between A and C? That is nothing but a distance between a corner atom, a center atom, and an atom at C. So R plus 2R plus R, so it becomes 4R. And what is AD? AD is nothing but a lattice edge, that is an edge length which is A, and AB is once again it's going to be an edge length which is A. So now we can find what is the value by using a Pythagoras theorem. So what is it? AD square is equal to AC square plus CD square. So we can consider any of the triangle. You can consider ABC or ADC. So both goes to be the same. So now I am just considering the triangle ABC. So here you can see that AC square is equal to AB square plus BC square. So now from this we can calculate what is R. So once again be careful when we are just going to substitute the values for AC, which is 4R the whole square. So 4R the whole square, it comes to be 16R square, which is equal to 2A square, or R is equal to A by 2 root 2. The last characteristic for FCC is APF, that is atomic packing factor, which once again explains the vacancy that is being present in an FCC unit cell. So how to calculate it? APF is small v divided by capital V, which is number of atoms in the unit cell divided by the volume of the unit cell into volume of an atom. So how to calculate it? So first we go for the numerator, which is small v, and number of atoms per unit cell is 4 into volume of an atom is 4 by 3 pi r cube divided by capital B. So here once again it is a cubic structure, so the volume remains the same, A cube. So APF is 4 into 4 by 3 pi r cube divided by A cube, and as we have calculated R as root 2 A by 4 or A by 2 root 2, we can just substitute that value in R and we get the value to be pi by 3 root 2, which comes to be 0.74. So which means 74% of the volume of FCC is occupied by atoms and the remaining 26% remains vacant. And this what makes FCC to be more closely packed structure in a cubic structure, and most of the metal exhibit this property, and this is called as a closely packed structure and has most of application when compared to other cubic structure.